seeds of life did the universe plant us here? In the infinite canvas of the universe, where billions of galaxies shimmer like islands of light in an endless ocean of darkness, one haunting question echoes through the silence of space. Are we alone? Humanity has stared at the stars for thousands of years, weaving myths, religions, and sciences around those distant points of light. The night sky has always whispered secrets beyond our grasp. Ancient civilizations thought of the heavens as the domain of gods, while modern scientists see them as a vast laboratory filled with potential. Yet the mystery that unites both the poet and the physicist remains the same. How did life begin? And perhaps more importantly, did it truly begin here on Earth? Earth, in all its beauty, seems like a fragile oasis floating in an unforgiving void. Our blue planet holds mountains, rivers, forests, and oceans that teem with life. But if we take a step back, zooming out into the cosmos, we realize how small, how improbably delicate our world really is. Among trillions of planets scattered across billions of galaxies, why did life spark here? Was it an accident of chemistry, a lucky convergence of molecules and energy, or was our world seeded, planted from the stars themselves? This question is not merely philosophical. It cuts to the core of our identity. To ask where life came from is to ask who we are, what our place is in the universe, and whether our existence is an isolated miracle or part of a grander cosmic pattern. In the early 20th century, science took its first serious steps toward answering the riddle of life's origin. One of the most iconic experiments was conducted in 1953 by Stanley Miller and Harold Urey. They attempted to recreate the conditions of early Earth in a glass flask filled with methane, ammonia, hydrogen, and water vapor, gases believed to be present in the primordial atmosphere. By running electric sparks through this mixture, mimicking lightning strikes, they produced amino acids, the basic building blocks of proteins. It was a stunning discovery. Life's essential molecules could arise from non-living chemistry. For many, this seemed like the answer. Life was not a miracle, it was chemistry obeying the laws of physics. Yet even as the scientific world celebrated, deeper questions arose. Amino acids are not life, they are just the alphabet. Where were the sentences, the paragraphs, the story of biology itself? How did simple molecules cross the vast chasm into complex, self-replicating systems like RNA and DNA? And perhaps the most haunting question of all, why here on Earth, of all places? The more we studied our planet, the stranger the puzzle became. Evidence suggested that Earth, in its earliest days, was anything but welcoming. 4 billion years ago, our world was a hellscape. The surface boiled under relentless asteroid impacts, volcanoes spewed toxic gases, and oceans of magma churned restlessly. How could fragile molecules of life survive in such chaos, let alone arise from it? If life began here, it did so under nearly impossible odds. And if the odds were so small, maybe life did not start here at all. This is where one of the most intriguing ideas enters the story. Panspermia. The hypothesis that life, or at least its ingredients, did not originate on Earth, but arrived here from elsewhere in the cosmos. The word itself comes from Greek, pan meaning all, and sperma meaning seed. It suggests that the universe is filled with seeds of life, drifting through space, waiting for the right conditions to grow. Imagine a cosmic gardener, scattering seeds across the galaxy. Some land on barren rocks, lifeless and sterile, while others find fertile soil, a planet with water, atmosphere, and the right chemistry. On those rare worlds, the seeds awaken, sprouting into ecosystems, evolving into creatures, and eventually perhaps gazing back at the stars, wondering where they came from. It is a poetic idea, but also one rooted in science. In 1969, a meteorite fell in Murchison, Australia. When scientists cracked it open, they found not only amino acids, but also complex organic molecules. These were not contaminants from Earth's soil. They were forged in the heart of space, carried inside a rock that had traveled for millions of years before crashing into our planet. Similar discoveries have been made in other meteorites, as well as in comets studied by space probes. The message is clear. The universe is not barren. It is rich with the chemistry of life. And yet, this raises an even bigger mystery. If space is filled with life's building blocks, are we the result of cosmic inevitability? Did the universe plant us here intentionally, or are we just one of many scattered sprouts that happen to take root? The fascination with this question is not confined to laboratories. Philosophers, writers, and thinkers throughout history have speculated about life's celestial origin. The Roman poet Lucretius, 2,000 years ago, described the universe as a fertile field where seeds of life rain down on worlds. In the 19th century, scientists like Lord Kelvin and Hermann von Helmholtz suggested that comets could deliver life across space. Today, the Panspermia theory continues to intrigue astrobiologists and cosmologists alike. But skeptics ask, even if molecules arrived here from space, does that really answer the question? Or does it just push it further away? If life's building blocks came from beyond Earth, where did they come from? Did they form spontaneously in interstellar clouds, in the icy depths of comets, or on some distant world long forgotten? The mystery grows deeper the more we chase it. Still, the allure of the idea persists because it reframes our place in the cosmos. Instead of being an isolated fluke, life could be a natural extension of the universe's creativity. Just as stars forge heavy elements in their fiery cores and scatter them through supernovae, perhaps the universe also scatters the seeds of life, ensuring that wherever the right environment exists, living worlds will bloom. This perspective transforms the way we look at Earth. No longer is our planet the sole cradle of life. Instead, it is one garden among many, tended by the same cosmic forces that shape galaxies and stars. To think of ourselves as children of the stars is not just metaphor, it might be literal truth. Our atoms were forged in supernovae, our molecules may have drifted here on comets, and our consciousness might be the universe reflecting on itself. The question then becomes, what does it mean for us as humans if we were seeded by the cosmos? Does it diminish our uniqueness, or does it expand it? On the one hand, it suggests that we are not an isolated miracle, that life might be common wherever conditions allow. On the other, it forces us to confront the possibility that we are just one branch of a vast cosmic tree, one sprout among countless others. Perhaps on another world, light years away, other beings very different yet born of the same seeds are also looking at their skies, asking the same question. And what if the seeds were not scattered blindly? What if panspermia was not just a natural process, but a deliberate act? Some scientists, like Francis Crick, co-discoverer of the structure of DNA, speculated about directed panspermia, the idea that an advanced civilization might intentionally send microbial life to other planets to spread biology across the galaxy. In this view, we might not just be cosmic accidents, but part of a greater design, a link in a chain of life stretching back to civilizations far older than humanity. Of course, such ideas border on speculation, even science fiction. But they reveal the depth of our curiosity, the hunger to connect our origins to something larger than ourselves. The universe, in its vast silence, invites these questions, even as it withholds its answers. Every time we look deeper into the cosmos, we find more clues, more puzzles, more hints that life is not confined to Earth. Telescopes detect complex organic molecules floating in the cold depths of interstellar clouds. Space missions uncover evidence of water and organics on moons and comets. And experiments show that life, at least microbes, can survive the harsh vacuum of space, riding inside rocks or ice for unimaginable distances. If this is true, then life is not fragile. It is resilient, tenacious, cosmic. It does not wait for perfect conditions. It seeks them out, adapts, and flourishes wherever it can. Perhaps this is the true secret of the universe, that life is not the exception, but the rule. As we return to our blue planet, spinning quietly in the Milky Way, we must confront the awe of this possibility. Our oceans, our forests, our bodies themselves may carry echoes of a journey that began far beyond Earth. We are, in a sense, the children of Stardust, the inheritors of a cosmic legacy written across light years. And yet, for all our knowledge, we are still left with a haunting uncertainty. Did life truly begin here, crafted from Earth's own raw materials? Or were we planted, like seeds drifting across the cosmic winds, waiting for a home? The stars above remain silent, but their silence is not empty. It is filled with the weight of this question, a question that defines us as a species, a question that will drive exploration, science, and imagination for generations to come. Because when we ask where life began, we are really asking where we began. And in the vast expanse of the universe, that answer may be more extraordinary than we dare to imagine. If the mystery of life's origin has always lingered at the edge of human thought, then the cosmos itself provides the stage upon which that mystery deepens. Part of the intrigue lies not only in what we know, but in what we suspect, that our planet may not be unique, that the conditions which sparked life here may be replicated across the galaxy. This possibility drives a new field, astrobiology, a science that blends astronomy, biology, chemistry, and geology into one pursuit, the search for life beyond Earth. It is a science both bold and humble. Bold because it seeks answers to the oldest question we ask when we gaze at the stars. Humble because it acknowledges how little we know. When we look at our solar system, we see hints everywhere. Mars, dry and rust red, once held rivers and lakes and perhaps shallow seas. Evidence from rovers shows ancient water channels, mineral deposits, even the chemical fingerprints of organics. It is not proof of life, but it whispers of possibility. Europa, a moon of Jupiter, hides a global ocean beneath its icy crust. Tidal forces from Jupiter's gravity churn its waters, perhaps creating hydrothermal vents not unlike those on Earth where life may have first thrived. Enceladus, a small moon of Saturn, spews geysers of water vapor and organic molecules into space from a subsurface ocean. Spacecraft have flown through these plumes, tasting their chemistry. Titan, Saturn's largest moon, is a world of methane lakes and hydrocarbon skies, a bizarre laboratory where chemistry runs wild in alien forms. Everywhere we look, we find places that could, in theory, host life, at least microbial life. And if our solar system is rich with potential, then across the galaxy, among the countless billions of exoplanets discovered in recent years, there may be worlds with oceans, atmospheres, and climates eerily similar to our own. The Kepler Space Telescope and later missions revealed that planets are not rare. They are abundant, perhaps more numerous than stars themselves. Among them, Earth-like planets orbiting within the habitable zone where liquid water can exist appear to be common. In other words, the conditions for life are not special to Earth. They are written into the very fabric of the cosmos. This realization forces us to reconsider panspermia not as an exotic theory, but as a natural extension of cosmic abundance. If the universe is rich with organic molecules, if planets and moons everywhere hold the potential for water and chemistry, then perhaps life is not a solitary flame, but a fire that sparks wherever it can. And if life can arise in many places, then perhaps it can also travel between them, carried by rocks, dust, and comets, leaping across the void like embers on the wind. The resilience of life on Earth lends weight to this idea. Microbes have been found thriving in the harshest environments imaginable, in boiling hydrothermal vents deep under the sea, in acidic hot springs, in frozen Antarctic deserts, in the radioactive ruins of Chernobyl. Some species, called extremophiles, can survive vacuum, radiation, and temperatures that would annihilate most organisms. Tardigrades, tiny creatures also known as water bears, have been subjected to space itself, surviving exposure to the vacuum and solar radiation for days, only to revive once returned to water. If such creatures can endure the brutality of space for even short periods, then it is conceivable that spores or microbes shielded inside rocks ejected by impacts could survive journeys between planets, perhaps even between star systems. Experiments have already tested this idea. In low Earth orbit, organic molecules have been exposed to space on satellites, and some survived for years. Meteorites from Mars, blasted off its surface by impacts, have been found on Earth, suggesting that planets can exchange material. If Mars once hosted life, then fragments of its biosphere could, in theory, have reached Earth, seeding our world. Conversely, Earth life could have traveled outward, perhaps even now resting dormant on Mars, awaiting discovery. Yet even as these possibilities expand our imagination, we must confront the limitations of our knowledge. Chemistry alone does not make biology. The leap from molecules to metabolism, from simple reactions to self-sustaining cells, remains shrouded in mystery. Scientists debate how this leap occurred. Some argue for a RNA world, where self-replicating strands of RNA were the first living entities. Others propose metabolism-first scenarios, where networks of chemical reactions gradually evolved complexity, while others imagine life emerging from mineral surfaces or deep-sea vents. Each theory holds fragments of plausibility, but none have closed the gap completely. And here lies the tension. If life arose independently on Earth, then perhaps it is rare, requiring conditions so precise that only a handful of worlds ever achieve it. But if life was seeded, either naturally by panspermia or deliberately by unknown intelligence, then the odds shift dramatically, suggesting that life could be widespread, even universal. The question resonates beyond science into culture and philosophy. Consider how our myths and religions often speak of life as a gift from the heavens. From the breath of gods in ancient Mesopotamia to the cosmic eggs of Hindu tradition, humanity has long imagined life as descending from above. Even in modern times, science fiction weaves narratives where alien intelligences guide evolution, or where humanity itself is an experiment planted on Earth. These stories mirror our longing for connection, our refusal to believe we are an accident in a silent universe. But the scientific approach, while cautious, has begun to brush against these ancient intuitions. In 2018, astronomers detected phosphine in the clouds of Venus, a gas that on Earth is associated with microbial activity. Though later contested, the discovery reignited the debate. Could life exist in places once thought impossible? Venus, with its crushing atmosphere and searing heat, seems hostile beyond measure, yet high in its clouds, conditions may be mild enough for microbial life. If life can adapt there, then it can adapt almost anywhere. And if life exists beyond Earth, then we must ask, did it start there independently? Or did we all share a common cosmic seed? This is the essence of panspermia. It does not claim to answer how life began, only that once it did, it could spread. In this view, the universe is not a collection of isolated experiments, but a network, a web of living worlds linked by drifting seeds across billions of years. To imagine this is to imagine kinship on a galactic scale. Life on Earth may be related, however distantly, to life elsewhere, not just in structure or chemistry, but in origin. The DNA that coils within our cells might share ancestral echoes with molecules far across the galaxy. If this is true, then our search for extraterrestrial life is not just about finding others. It is about finding family, long-lost cousins scattered by cosmic winds. Still, we must tread carefully between wonder and evidence. The allure of panspermia is powerful, but science demands proof. Meteorites with organics are suggestive, but not definitive. Microbes surviving space conditions are compelling, but not conclusive. The gulf between plausibility and certainty remains wide. And so the work continues. Missions to Mars, drilling for ancient organics, spacecraft to Europa, and Enceladus hunting for biosignatures in alien oceans. Telescopes scanning exoplanet atmospheres for chemical signs of life. Each experiment brings us closer to an answer, though perhaps the answer will raise even deeper questions. For if we do discover life beyond Earth, microbial or intelligent, we will face the ultimate test of panspermia. If their biochemistry mirrors ours, if their amino acids, their genetic codes, even their molecular handedness match, then it may suggest a common origin, a cosmic seed shared across worlds. But if their life is entirely different, built on other molecules, then panspermia may be a smaller piece of a larger story. Life arising again and again, everywhere conditions permit. In either case, the discovery would transform us. To know we are not alone, to know that life blooms across the universe, would reshape philosophy, religion, and identity. And if we are connected, seeded by the cosmos, then our sense of belonging expands beyond Earth, beyond the solar system, into the very fabric of the galaxy itself. This is why the question of origins is not merely scientific curiosity. It is existential. It touches on the human need to belong, to understand our roots, to place ourselves in the story of the cosmos. Every culture has myths of beginnings. Every child asks where they came from. Every civilization seeks its origin. To discover that our beginning lies not in the soil alone, but in the stars, would be to rewrite the oldest story of all. And so we continue, building instruments, sending probes, constructing theories, writing equations, all in pursuit of an answer whispered in the silence of the night sky. We chase meteors. We dig into Martian dust. We listen to radio waves from the stars. We stare through telescopes at worlds unseen, all driven by the same yearning that guided the first humans who traced constellations on cave walls. Perhaps, in the end, the truth will be both stranger and simpler than we imagine. Perhaps life arose here, in the crucible of Earth, and simultaneously there, in countless other crucibles across the galaxy. Perhaps seeds are not scattered, but inevitable, emerging wherever conditions allow. Or perhaps we truly are seedlings planted by forces beyond our comprehension. Whatever the truth, its discovery will not diminish us, it will enlarge us. For in seeking the origins of life, we are seeking not only where we came from, but where we might go. To know that the seeds of life can travel the stars is to imagine that one day we too may carry them further, spreading life intentionally, making panspermia not just a hypothesis of the past, but a mission for the future. Humanity then becomes both the question and the answer, seeded by the universe and destined to seed it in return. If the idea that life may have been seeded from the cosmos challenges our imagination, then the search for its traces tests our persistence. The journey to understand origins is not only about the chemistry of the past, but also about the evidence we can find in the present. Our world itself holds clues, locked within the deepest rocks, the oldest fossils, and the most extreme habitats. The stars may whisper possibilities, but Earth retains the record of its first stirrings. If we can read it clearly, we may uncover the blueprint of beginnings. Geologists have uncovered microfossils dating back nearly 3.5 billion years. Within ancient rocks in Western Australia and South Africa lie the remnants of primitive microorganisms that lived in shallow seas. These fossils show that life arose relatively quickly after Earth stabilized from its violent birth. The implication is striking. Once conditions allowed, life did not delay. It emerged with determination. Was this rapidity evidence that life naturally arises wherever it can? Or does it suggest that the seeds had already been planted, waiting for fertile ground? The chemical signatures of early life provide further hints. Carbon isotopes in ancient sediments show fractionation consistent with biological processes, pointing to microbial activity long before the fossil record becomes clear. Stromatolites, layered structures created by colonies of cyanobacteria, appear in rocks nearly as old as the Earth's oceans themselves. These microbial mats not only lived but transformed the planet, slowly oxygenating the atmosphere, paving the way for complex organisms. The story written in stone reveals not hesitation, but inevitability. Yet even as we trace the earliest evidence of life, we encounter paradoxes. The building blocks of biology, such as amino acids and nucleotides, are fragile under harsh conditions, yet somehow they endured and assembled in an environment that was anything but gentle. Ultraviolet radiation from the young sun, asteroid bombardments, and volcanic eruptions created a turbulent stage. How did molecules not only survive, but organize into systems capable of self-replication? Some scientists suggest protective niches, such as hydrothermal vents at the ocean floor, where mineral structures could shield and catalyze reactions. Others imagine shallow pools, where cycles of wetting and drying drove the polymerization of nucleic acids. Still others turn their gaze outward, arguing that meteorites may have delivered both ingredients and stability. The truth may be a combination of all these pathways. Our exploration of life's beginnings is complicated by the fact that all living things on Earth share the same fundamental biochemistry. Every organism uses DNA or RNA as the carrier of information, the same 20 amino acids to build proteins, and the same universal genetic code. This unity is powerful evidence of a single origin, a last universal common ancestor that lived billions of years ago. But it also erases the record of diversity. If other forms of life ever arose independently on Earth, they have been outcompeted or absorbed into the dominant lineage. We are left with one survivor, one branch of the tree, making it impossible to know whether life could have begun in multiple ways or whether its spark is far rarer than we imagine. Some scientists speculate about the possibility of a shadow biosphere, a hidden form of life on Earth that uses alternative biochemistry. Perhaps different amino acids, different nucleotides, or even different solvents instead of water. If such life exists, it would suggest that the origin of life is not a singular by improbable event, but a repeating process that can occur under varied conditions. So far, no definitive evidence has been found, but the search continues in the most unusual environments, from saline lakes to deep subsurface ecosystems. Meanwhile, our investigations extend outward because other worlds may preserve records that Earth has lost. Mars, once warmer and wetter, may still hold fossils or chemical traces in its ancient rocks. Missions like Perseverance are designed to drill and cache samples for eventual return, allowing us to probe the Martian past. If we find evidence that life once existed there, the implications will be profound. If Martian life shares our biochemistry, then panspermia may be the link. Perhaps we are relatives, one planet seeding another. But if it is different, if its genetic code is alien, then life is not singular, but multiple, arising independently wherever conditions permit. Either way, the answer would shake our understanding. Beyond Mars, Europa and Enceladus tempt us with their hidden oceans. Probes may one day dive into the plumes of Enceladus or burrow through the ice of Europa, searching for biosignatures, molecules that reveal metabolism. Even Titan, with its methane rivers, may harbor exotic forms of life that do not resemble our own. These missions are not just technological marvels, but philosophical expeditions, seeking to answer whether life is Earth's exclusive treasure or the galaxy's common currency. While we wait for these journeys, we also look outward with telescopes. The James Webb Space Telescope has begun to analyze the atmospheres of distant exoplanets, searching for chemical imbalances that could indicate biology. On Earth, life creates signatures such as oxygen, methane, and carbon dioxide in specific ratios. Detecting such patterns elsewhere may be the first indirect evidence of alien ecosystems. And if those signals are found repeatedly across many worlds, then the conclusion becomes difficult to resist. Life is not unique, it is universal. But what if we find nothing? What if every search returns silence, every rock barren, every atmosphere sterile? Then the paradox sharpens. If Earth is alone, then life's emergence is far rarer than we hoped. It would mean that among trillions of planets, ours alone blossomed. Such solitude would make life all the more precious, but also all the more fragile. In that case, perhaps panspermia is not the answer but the hope, that we ourselves may one day carry life to other worlds, ensuring that the spark does not fade. The philosophical implications of these possibilities are vast. If life is common, then intelligence may be common, and the universe may teem with civilizations, some perhaps older and wiser than ours. If life is rare, then our responsibility to preserve and extend it becomes enormous. We may be the sole conscious voice in a silent cosmos. Both scenarios challenge us, forcing us to redefine meaning, purpose, and destiny. There is also the possibility, whispered by some scientists and embraced by dreamers, that panspermia was not only natural, but intentional. If an advanced civilization once seeded planets with life, then we are part of a lineage that stretches beyond Earth and even beyond biology itself. We would be not merely children of Stardust, but descendants of intelligence, heirs to a deliberate project of cosmic cultivation. Such speculation treads into territory where science and philosophy overlap, where data gives way to imagination. Yet it remains a haunting thought. Perhaps our search for origins is not just about chemistry, but about communication, about deciphering a message written into the molecules of life themselves. The double helix of DNA, with its elegance and efficiency, often inspires such wonder. Could its universality be coincidence? Or does it reflect a design, natural or otherwise, intended to propagate across the cosmos? Francis Crick himself, though cautious, entertained the possibility of directed panspermia, not because he believed in it, but because he recognized the improbability of life arising spontaneously in the narrow window Earth allowed. The idea lingers at the edges of science, never proven, never disproven, always provocative. Yet, even if life was seeded, we return to the same ultimate question. Where did the first seed come from? If panspermia spreads life, it does not explain its genesis. It only relocates the mystery. Somewhere, in some corner of the cosmos, the leap from chemistry to biology had to occur. Whether it happened once or countless times remains the greatest unknown. Perhaps we will never know. Perhaps the origin lies forever hidden in the mists of time, lost in events billions of years old. But the pursuit itself gives us meaning, because in asking, we define ourselves as seekers, as participants in the cosmic story. As we grapple with these questions, we cannot ignore their impact on human imagination. Literature, art, and myth have long anticipated the scientific debates. From the cosmic eggs of creation myths to modern films about extraterrestrial contact, humanity has always sensed that our beginnings are tied to the stars. Science gives rigor to these intuitions, but it does not erase their wonder. In fact, the more evidence we gather, the more extraordinary the universe becomes. The discovery of organics in space, the detection of habitable planets, the survival of microbes in vacuum. Each finding strengthens the narrative that life is not an anomaly, but a cosmic theme. And still, the silence persists. No signals from intelligent civilizations have been confirmed, no alien fossils unearthed, no undeniable biosignatures detected. We exist in a tension between abundance and emptiness, between hope and solitude. This tension is what keeps the question alive, what fuels our telescopes, our probes, our theories. It is the silence of the stars that drives us to listen harder, to look deeper, to dream further. In the end, part of the allure of the question is that it unites science and spirit, logic and imagination. To ask whether life was seeded from the cosmos is to blend evidence with awe, reason with wonder. It is to stand on the shores of the infinite, gazing outward, knowing that the answer may never come, yet unable to stop asking. Because in the act of asking, we become more than observers. We become participants, voices in the cosmic dialogue, seeds ourselves, destined perhaps to spread and continue the cycle. As we stand at the edge of discovery, the question of whether the universe planted the seeds of life here on Earth becomes more than a poetic idea. It is a challenge to our very sense of belonging. The narrative that began billions of years ago with hydrogen atoms swirling in cosmic clouds is still unfolding. We are characters within a cosmic drama that has not yet reached its conclusion. When we look up at the stars, we are not simply gazing at distant lights. We are searching for mirrors, for reflections of ourselves scattered across the galaxies. The thought that life could exist beyond Earth is not a distant fantasy anymore. It is a scientific pursuit, a technological frontier, and perhaps a spiritual awakening. Imagine a future where telescopes can peer so deeply into exoplanetary atmospheres that they reveal unmistakable biosignatures, oxygen, methane, or complex organic molecules dancing in the light of alien suns. The James Webb Space Telescope has already shown us that we can analyze the faintest signals of worlds light years away. In time, the tools will sharpen and the mysteries will yield. A single detection of life, no matter how small, even if only microbial, would rewrite every philosophy, every theology, every history book. Humanity would no longer ask if we are alone. We would ask instead, how many others are out there, how different they are, how similar they may be. Yet the search is not limited to telescopes. Robotic explorers roam Mars, drilling into rocks and analyzing soil, hoping to find whispers of ancient rivers or fossilized microbes. Beneath the icy crusts of Europa and Enceladus, oceans of liquid water wait in the darkness. Warmed by tidal forces, rich in chemical energy, and shielded from harsh radiation, they might harbor ecosystems as complex as Earth's own hydrothermal vents. Someday, spacecraft will dive into those hidden seas, sending back the first images of alien organisms swimming in the black water. The moment that happens, the seeds of life will no longer be a theory. They will be a living revelation. The possibility stretches even further. What if life is not rare, but abundant? What if the galaxy is seeded not with one lonely garden, but countless blooms of biology, each evolving in strange directions? In such a cosmos, the idea of panspermia, life spread by comets, asteroids, or interstellar dust, becomes less of a speculation and more of a universal principle. If life is indeed woven into the very chemistry of the universe, then Earth is not unique. It is one among many. It is a single note in a vast symphony of existence. That realization does not diminish us. Instead, it magnifies the wonder of being alive in a universe where life itself is a cosmic inevitability. And yet, a haunting question lingers. If the universe has seeded life everywhere, where are they all? The silence of the skies, known as the Fermi paradox, still looms over us. Perhaps civilizations rise and fall like waves. Perhaps they destroy themselves before they can reach the stars. Perhaps they exist but remain hidden, cloaked in technology beyond our comprehension. Or perhaps the seeds of life are plentiful, but the flowering of intelligence is rare, fragile, and fleeting. We may be among the first or among the few. If so, then the responsibility is immense. Humanity itself becomes a carrier of seeds. As we launch probes beyond the solar system, as we dream of colonies on Mars and beyond, we are unknowingly enacting the role of cosmic gardeners. The DNA we carry, the microbes on our skin, the culture encoded in our languages and art, all of it is a continuation of that ancient spark that began long before Earth existed. We are the messengers of biology, the transporters of memory, the vessels through which the universe ensures that life will not remain confined to one fragile planet. But beyond science, beyond the equations and telescopes, lies the emotional weight of the question. If the universe planted us here, what does it mean for the purpose of existence? Are we an accident? Are we a deliberate outcome of natural laws? Or are we something in between, an emergent inevitability that was always destined to awaken and ask questions? The very act of wondering ties us to the cosmos in ways that transcend data. To know that the atoms in our blood were forged in stars, to know that the carbon in our cells could once have drifted between galaxies, to know that the story of life may be written into the fabric of space-time itself. This is both humbling and exhilarating. As the search continues, we find that the journey is as important as the answer. Each experiment, each discovery, each photograph of a pale blue dot from the edge of the solar system reminds us that the seeds of life are not only about origins, they are about futures. Every time we decode a strand of DNA, every time we model the chemistry of interstellar dust, we are piecing together fragments of a puzzle that stretches across eons. Whether or not we ever find alien life, the pursuit itself reshapes us. It unites nations, inspires generations, and fuels a sense of wonder that no boundary can contain. So we return to the question, did the universe plant us here? Perhaps the universe did not plant us in the way a gardener plants a seed. Perhaps instead, it created the conditions, the soil, the water, the sunlight, and then allowed nature to take its course. Perhaps Panspermia spread the molecules. Perhaps Earth alone kindled the spark. Perhaps both stories are true in different ways. What matters is not only how we began, but what we choose to do with the knowledge that we are part of something greater. In the silence of the night sky, the stars continue to burn. Galaxies spin in their endless dance. Comets streak through the darkness carrying ancient ices. And somewhere perhaps life is looking back, asking the same question we ask now. In that symmetry, in that possibility, lies the true beauty of the mystery. We are not merely observers of the cosmos, we are participants, children of Stardust searching for our kin. And so, as the narrative closes, we realize it is not an ending, it is an invitation. To look deeper, to listen more carefully, to imagine with courage. The seeds of life may be scattered across the universe, waiting to bloom, and perhaps, in time, we will find them. Until then, we carry the responsibility, the wonder, and the hope of being alive here and now in a cosmos that may be far more alive than we ever dared to dream.